Okay. Yeah. So thank you to Ricky Chung for the lecture. And so next, it's me doing a. Sorry about that. So next, the next part is gonna be me doing a lecture on the pigeonhole principle. And so yeah. Oh, okay. Yeah. So the pigeonhole principle. And so the most basic form is basically if there are n plus 1 pigeons and they're distributed into n pigeonholes, and that's where the name pigeonhole principle comes from in the first place, then there is always at least one pigeonhole that has at least two pigeons. And so a proof for this would be something like this. So, oh, sorry about that. So, yeah, so a proof for that would be something like this. So basically, we are assuming for the sake of contradiction that all pigeonholes will have at most one pigeon. And so we're trying to prove that this is false. And so the way you can do this is that the number of pigeons is at most n times 1 because there's n holes and each hole has at most 1. And so the number of pigeons is at most n. However, you're also given that there are n plus 1 pigeons. And so that leads to a contradiction. And so there must always be at least one pigeonhole with at least two pigeons. And so now another form, and it's not as basic, would be is known as the generalized pigeonhole principle. And it's quite similar. But it states that when n times k plus 1 pigeons are distributed into n pigeonholes, there is at least one pigeonhole with at least k plus 1 pigeons. And so the proof for this is really quite similar to that of the basic pigeonhole principle that was written up there. And so we're just assuming that all pigeonholes have at most k pigeons. And then once again, we're finding the number of pigeons that the pigeonholes can fit. And that is less than the number of pigeons that we are given that there are. And so that leads to contradiction, and that proves this form of the pigeonhole principle. Okay. And so now, as for applications and strategies for the pigeonhole principle. And so the pigeonhole principle can be used in many different ways, and it can be done over a wide variety of topics. And so oftentimes the most difficult part of the pigeonhole problems will just be identifying which aspect of the problem is the pigeonholes and which parts are the pigeons. And sometimes you need to make up which parts are the pigeonholes in order to solve the problem. And so, and if it is at all possible, it's better to reduce the number of pigeonholes that the pigeons are distributed into, and even if some casework is necessary. And so after this, I have a few example problems for the pigeonhole principle. And so for each problem, I'll give a short while for people to try them on their own before I start explaining how you would solve one. And if you ever get an answer, feel free to private message me in the chat. So this is Okay, so I'll start going over this example. So there are a total of 6 pairs of red socks, 9 pairs of orange socks, 3 pairs of yellow socks, 4 pairs of green socks, 8 pairs of blue socks, 7 pairs of white socks, and 5 pairs of black socks in my drawer. And so basically we're just drawing out the socks randomly, and so I want to guarantee 4 pairs of socks. And so the way this works is that I'm drawing the socks out one at a time. So the least optimal case would be 7 socks for, and there are a total of 1, 2, 3, 4, 5, 6, 7 colors. So 7 socks for 6 colors, and 8 socks for 1 color. And so this is obviously the worst case. And so, however, there are only 3 pairs of yellow socks, so we can basically take out another sock from this. So 7 socks for 5 colors, and 6 socks from 1 color. And so this is the absolute worst case scenario for when you're drawing out the sock. And so now the number of socks that are drawn out is just 7 times 5 plus 8 plus 6, which is 35, plus 8 plus 6, which is equal to 49. And so did anyone have any questions about this problem or how you would do it? Okay. Well, I don't think so. So here's the next question. And so once again, feel free to send me answers if you get them, or in this case, proofs. Okay, so now for this question. So in order to find out the preferences, there are 65 teachers, and so they need to fill out this form. And so the form is a total of 6 questions, and each question is yes or no. And so we're trying to prove that there are 2 people with identical responses to those 6 questions. And so, first of all, we can find the number of possible responses, and that would be the number of pigeonholes. And so, there are a total of 6 questions, and each question is yes or no. And so, each is yes or no. And so, basically, there's a total of 2 possibilities for each of these 6 questions, and they're all independent. And so what that means is that there are 2 to the power of 6 ways to respond to these questions, and this is equal to 64. However, there's a total of 65 teachers, and so by the pigeonhole principle, we can see that there are 2 teachers or people that have identical responses to the question. And so does anyone have any questions about how this problem is done? Oh, okay. It doesn't seem like it, so next question. Okay, well, this problem isn't that hard either, so I'll start going over it. So I'm picking a total of 11 random positive integers. And so show that no matter how I pick them, there always is a pair, and their difference is a multiple of 10. And so how this works is actually pretty simple. So actually, the only thing that matters is just the units digit. So whether it's 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. And so there's 11 random positive integers chosen. And so that means that at least one of these 10 boxes will have 2 of them that are the same. And once we take the difference of 2 integers with the same unit digits, then the resulting number is always a multiple of 10, because the difference of 2 numbers with the same unit digit and then the digit 0, and that's a multiple of 10. So does anyone have any questions about this problem? Okay, then let's go on to this one now. So once again, please send me answers if you ever get any. Okay, I'll start going over this problem. So I have a board and it's in the shape of a regular hexagon. And so it would look something like this. Yes. And so now I'll show that no matter, and each side is 5 inches. Well, the exact number here doesn't really matter. It just has to be the same as this. And so show that no matter how I throw 7 darts onto the board, there are always 2 darts that are separated by a distance of at most 5 inches. And so how this works is basically we're dividing this hexagon into 6 pieces. So 1, 2, 3, 4, 5, and 6. And so each of these pieces is an equilateral triangle with side lengths of 5 inches. And so there are a total of 7 darts, or 7 points. And so there is always one equilateral triangle in which there are 2 points. And also the longest distance between any 2 points in the equilateral triangle is between the 2 vertices, and that is a total of 5 inches. And since the only requirement for the distance is at most 5 inches, that just proves the problem. So does anyone have any questions about this problem? Okay, well, don't think so. So let's move on to the next question. Okay, so I'll start going over this question now. And so there are 51 points, and there's a square with side lengths of 5 feet. And to prove that some 3 of the points can be covered with the square of side length 1 foot. And so the way this works is, first of all, we can draw the square. Okay. And so, sorry. And so now we can divide this into 25 smaller squares. This might be a bit badly drawn, but yeah. well, yeah, I should look something like this. So this is 25 squares, and so there are a total of 51 points. 51 points and 25 small 25 small squares. And so by the pigeonhole principle, that means that some square has 3 points. And each of these squares is a total of side length 1 foot because there are 5 of them per side and they're all congruent. And so that's a square of side length 1 foot. And so that just directly proves what we wanted. And so now we can go to the final problem that we had for the pigeonhole. And so yeah, once again, I'll give you a while to try this on your own, and then I'll start explaining it. Okay, so yeah, I'll start explaining this problem now. So we're given a set of any set of 10 distinct 2-digit numbers. And so we're trying to prove that there are 2 subsets in this that share no common elements and they have the same sum. And so first of all, we can find the number of possible sums that there are. And so obviously the minimal possible sum is just 10. It's just 10. And that's because a subset cannot be non-zero. Or at least that wouldn't make any sense. Because there obviously won't be another subset with 0 elements in it. And so the maximum possible subset is 99 plus 98 all the way equals 90. And so the exact value of this number doesn't really matter. And all that's really necessary is that this is something less than 1000. And so that means that the total number of possibilities, or basically pigeonholes, pigeonholes, is less than 1000. And so, and there are a total of 10 distinct. So the total number of possible subsets of the 10 numbers are to the 10 minus 1. Well, the minus 1 is because we can't include the empty subset. And we should know that the number of subsets of a set of n elements is exactly 2 to the power of n. And so what that means is that there are more pigeons than the number of pigeonholes. And so basically, oh, and this is greater than, this is equal to 1024. 1023, sorry. And so what that means is that there definitely exists 2 subsets of the numbers that have the same sum. However, we aren't guaranteed that they have no common elements. And so the way to make sure that the 2 subsets are disjoint or they have no common elements is pretty simple. We just take out all elements that they have in common. And the sum of the subsets would still be equal, although the sum itself would change. And so yeah, that concludes this problem, I guess. And so now we can have now we are going to explain the solutions for the level